Okay, recorded. Okay, good. So anyway, COMSOL give you a pretty good feature of seamless integration with Matlab, because historically COMSOL has been part of Matlab, part of a toolbox from Matlab, and then they're doing so well they decide to like go out and then become a separate company. So like deep down they're based on like Matlab code, so that's why they can integrate with Matlab so well. But anyway, so this is the very simple thing I've created before, a one-dimensional waveguide. Okay. Uh, here we have a small structure in here. I think I put it as air, right? Okay. So this waveguide is made of PDMS in water, and I've just added an air component in here. So you can imagine if I have a piece of, well, I have a small bubble. As long as I excite the bubble at the right frequency, the bubble can resonate. And in this case, the bubbles, let me see, the bubble's compressibility act as the spring, and the radiation impedance act as the mass. So there's a spring mass system. There's a single degree freedom oscillator. And you can imagine when it's resonating, it's interacting with the incoming sound so violently that they can do a lot of things with sound, mostly block the sound at the particular frequency. Anyway, here's a small waveguide. I can create this L, the length, right? R reference. This is the reference radius of the bubble I want to create. Anyway, there's a R1, AA, anyway. So these are just some parameters I create to try to create this geometry. Okay. And in here, geometry, rectangle, let's say rectangle, and then build a circle, and then build everything, build all, right? And then for the material, air and PDMS. In this case, I'm using a full microphone method. I've covered in class. I think both of you have learned that. Also, Stuart also covered this part in his class, right? Two microphone method and full microphone method. Yeah. So in this case, I'm having the microphone 1 here, microphone 2 in here, 3 and 4. Right. So these are the 4 positions of microphone. The idea is if I record, if I do 2 different experiments, record these 2 microphones, I can use the transfer matrix method to infer what is the impedance of the corresponding impedance of these small air bubble. Okay. So that's why I did like 2 experiments. Well, the first experiment, the first one is the pressure acoustics frequency domain, right? I'm putting a hard boundary here on the side, right? And have a plane wave radiation on both sides, and then have the incident wave from the bottom. So in this case, I have a wave coming in from the bottom and then propagating in the waveguide and then exit from here. Because it is a radiation boundary, there's no plane wave radiation boundary, there's no reflection. Okay. In the second experiment, I'm having a hard boundary, not only on the sides, but also at the bottom here. So it's a total reflection boundary. Now I have 2 different boundaries, 2 set of experiments. Then I can get the pressure at these 4 microphones and then calculate the corresponding impedance at this boundary, right? So well, normally when you do it, you have to calculate it in the in COMSOL, right? And do the mesh, of course. I mesh pretty fine, right? And do the mesh and do the study, right? The frequency domain, I'm calculating both cases. The first case is non-reflection boundary. The second case is total reflection boundary, hard boundary, right? And then I will have to, like, after calculation, I'll have to use the derived values or something, right? You can see here. Let's see. If I just calculate, it should take no time, pretty fast. Yeah, pretty fast, right? So all of these derived values, right? You can see point probe expression. This is the expression from data set is microphone 1. Okay, and the expression is ACPR PT is the total acoustic pressure. Similarly, if I have the second one, right, the microphone 2, 3, and 4. And then I just copy paste everything, but change everything into ACPR2.pt. So ACPR2 correspond to the second case. ACPR correspond to the first case. Okay, so you can see I have 8 different measured probes. Okay. Normally, you can just calculate everything. Let's say clear and evaluate all, override, right? You have all of these parameters available, right? You just copy and paste into MATLAB your own code. You calculate everything, right? And you can see, okay, what is the corresponding impedance of this bubble, right? That's normally what you do. But on the other hand, we can do it with MATLAB entirely directly. So what we can do here is after we create this model, calculate all this model, right? We can, when we do the export, you can see we can save as. Save as, there's an option of MATLAB file .m. Okay. When you save this .m file, let's say random, whatever. I think I got a typo. But anyway. When you save everything in the MATLAB file, you can just open it with a MATLAB. Okay. So basically, when you save it, it's actually saving every single step you have made, including all of these wasted steps. Like that is meaningless. So that you can see it's making this MATLAB file pretty long. Well, why is it so slow?
It's saving the data on it? Or...
No, it's saving every single step you take. Let's say if you when I open it, you can see it. So yeah, so for every single step, it's saving as a Java code actually. Okay, you see the import. So this is directly saved, well, created by the console, right? I cannot fully understand Java at all, but I can understand what it's saying, right? You can see it's creating a model path, right? And model parameter set, right? I'm setting L as 15 millimeters. I'm setting this R reference as 0.2 millimeters, something like that. And you can do it like that. So the good thing about this MATLAB file is that you can just define your like parameters directly in here. Let's say AA equals 12, right? I can just say model parameter here. I can say AA, and here I can say like a number 2 string. So number 2 string. AA, right? So now your COMSOL simulation becomes a like MATLAB function. So that means you can use this COMSOL simulation as a function in MATLAB and call it like a million times afterwards. Okay. And in this case, yeah. Oh, because it's accepting strings. This language, it only accepts strings. Yeah. For example, in the future, if you want to like calculate, let's say, change this let's say, model of AA as your input, right? If you see this AA is your input, then you can just use another MATLAB code and use like model AA So it will calculate everything for you and give you a feedback. So you can just run it without without even opening the COMSOL main file at all. Okay. So like when you do this step, also you see it's creating all these rectangles, right? You can just like copy and paste geometry and set this create like R1 rectangle and set this R1 to have the position 0 minus L/2 and also the size R cell and L. So this is how you create a rectangle and also how you create a circle, right? You can just create a circle like that. All of those views, right, it's kind of like a trash. You don't even need it. This is because when I save the Matlab file, I directly save it without cleaning the history, right? And also here, physics, you can create any like boundary conditions, right? This is the physics pressure acoustics, right? Based on geometry one. And then here you can see this create plane wave radiation, and the selection. This is the boundary for a selection, right? And then similarly, you can select the incident plane field as one, right? And then similarly, doing all of these stuff. After this, you can also say, yeah, create these probes, right? Domain probes. But anyway, all of the steps I've taken is recorded in here. Okay, you can just try to create your own file with all of these recordings. But as you can see, this file is still pretty long. It doesn't really need 300 lines. Okay, what you can do instead is that every time you create this file, like you do whatever modification you want, and until the end, you kind of have this file finalized, right? What you can do here is you can have a file. There's a command called compact history. When you do the compact history, wait for a minute or so. Yeah, see, compact history. Once you have this history compacted, then you can save as, you can call that a Matlab file single layer random 2 or whatever. Okay. Now, if you open it, you can see this file is only 250 lines. So it's actually helping you clean up the history and make the least amount of commands to create your file. Okay. Yeah. So I'll just show what I have here, single layer. You see, this is the file I created, and I just save it and then do all the manipulations. Let's see here, the single layer AA. I just call this the function single layer, and AA is my input, and AA is the size of bubble is AA times R reference. Okay, so in this case, I'm using Matlab to control the size of my bubble to see, okay, if I sweep the bubble size, how does the impedance change? Okay. And in here, you can see I'm defining the positions of my probes, the microphones, X1, X2, X3, X4, right? I'm defining the X01, X02 is both 0 because I only have one specific boundary at X equals 0. I don't really care about the size. And the frequency I care about is 200 kilohertz. Sorry, 20 kilohertz. Right? And then I can set my rho and C, everything, and calculate the K and calculate the Z. Okay. And here you can see here, right? I can set this parameter as L and R reference and everything here, and then set the R parameter as number to string AA times RREF. So in this case, I'm just creating just a string, like combining two strings together into one simple string, right? And after that, everything will be the same, right? Just create the geometry, create everything in here. Actually, all of these view sets, you can just delete it. Okay. Again, material library, right? You set these materials, right? once you set everything right here, label, Mac1, Mac2, they're all created automatically. Create a study, right? Study number 1. And then in here, numerical set, similar here. You just, anyway, in here, you can also like set the frequencies directly by changing the string in here. You just define everything. Yeah, this command just let you run the simulation. So this command will take the most amount of time. Okay. And these data sets, I don't really care about these data sets. But once you have all of those probes, right? Point evaluation. So PEV1 is the point evaluation one, right? And then this command tell you model result numerical point evaluation one. So this is the microphone number 1, get complex. So this is giving me a complex number. Well, it's actually not giving me a complex number, but giving me a like 1×2 matrix. The first element is the real part, second element is the imaginary part. And then I can say, okay, P11 is P111 plus I times P112. So I'm converting into a pure complex number. Similar here, right? Everything in here. And then P21, the same, right? PV5, 6, 7, 8. So from here, I can directly access whatever is calculated inside the COMSOL simulation. Okay. After that, you can see this is does it look familiar to you? I've covered in class, right? So exponential minus jkx1, jkx1 minus jkx2, jkx2. Similarly, minus jkx3, jkx3 minus jkx4 plus jkx4. Right? And then just HAB, HCD. Well, this is the HAB inverse times this P11, P21, P12, P22. And then this will give me my AB matrix and CD matrix. So A and B is the forward and backward propagating wave in tube 1. CD is the forward and backward propagating wave in the second tube, right? With the AB and CD, I can calculate the pressure and velocity on both sides of the bubble at x equals 0, right? So this is H01, right? You're calculating it 0, 1. Anyway, the PV matrix divided by another PV matrix, it gives you the transfer matrix. And after you have the transfer matrix, I can say, okay, this is my output. So in this case, if I just run it in the Matlab directly as a function, okay, single layer AA1, it will just run it and then spit out the matrix for me. So I don't have to open the COMSOL file at all. Okay. The only thing you need to care about is normally when you open the Matlab, it cannot read the Java code. But when you install the COMSOL, there is a COMSOL Live Link Matlab. I'll just close it. Right, there's a COMSOL Live Link Matlab here. Johnson, you haven't set it up yet, right? Well, anyway, in here you just like create a arbitrary login username and passcode. You just create 1, 2, 3. Yeah, 1, 2, 3. The passcode. Is it okay? Confirm passcode 1, 2, 3. It'll be fixed forever. Unless you uninstall everything. Okay. Yeah. So when you open it, it will just it will only ask for the username and password for the first time. And then when you open it, it will open the Matlab directly. Okay. So if you have this opened, now it can read the Java codes. So that means uh, editor run. I'm running just to change a folder. Okay. Because it cannot run at all because there's no A input. But let's say single layer 1. Okay. 1 times the size of my reference bubble. If I just hit run, it should be spitting out a matrix for me. Yep.
So, you already like set up this X1 to see like already in the console.
Yeah, already set up in the console. It's here.
Why?
Oh, because like when I use the for macro method, I need this information. So I have to make sure everything is the same.
Oh, you just wrote it down.
Yeah, I just wrote it down. Yeah. If you want, you can just write it in here and encode it directly to the.
So use that as my console.
Yeah, exactly. Do you see? Once I put in number 1, it would directly spit out the transfer matrix for me. Yeah. In this transfer matrix, you can see well, answer. Look right there. This way. Because I have a bubble, basically. Right. If you look at these 4 numbers, this one is very close to 1. Well, normally if I have a bubble, I know this is a monopole response. It will only, well, at this boundary, the pressure is not continuous, but the velocity is continuous. Okay, the velocity is continuous, but the pressure is not. So that means I should, if I write it down into a transfer matrix, the 1, 2 term should be some, let me see, 1 over y. The 1, 2 term and 2, 1 term are the more important terms. And actually for the 2, 1 term, it should go to 0, and 1, 2 term should be non-zero. And as you can see here, it give you e to the times 3/3. So it's 3,000 something. In here is almost negligible. And also you can see this is almost purely imaginary because the real part is negligible. So this is exactly how you typically model a small bubble inside the tube. Now, if you have a membrane instead of a bubble, right, across the membrane, again, the velocity, oh, sorry, my bad. For a bubble, the pressure is continuous on both sides, but the velocity is not continuous on both sides because some of the velocity is going into the bubble during the resonance. If you have a membrane, then the pressure, the velocity is continuous, the pressure is not continuous. So you have a non-zero component in here. But anyway, whatever it is, you can just set up the COMSOL, convert it into a Matlab file, and then like just modify everything inside the Matlab file. And with that, there are a lot of things to play with, right? Yeah, for example, I in some of the pretty complicated models I've created before, I have like 200, 300 boundary conditions I want to control. I cannot just put in my own hand. That would be a lot of errors. So what I did is I just create the COMSOL file in the most general case, and then select the boundaries by calculating their coordinates. So that I can always make like using the for loops. So I can always make sure every time I update all these boundary conditions, everything is updating well. Yeah, and with hand, it will be such a big pain to do. Yeah. So yeah, there are a lot of cool things to play with using COMSOL Live Matlab. And in the future, I will highly suggest you whenever you create this whole thing, then you can just do it. Another good thing about it is, okay, I have already created everything, right? Now I have find a good set of parameters in the Matlab, right? And I want to see, okay, how does it perform in the COMSOL file, right? What I can do here is I can still create everything in here, and just before the last line, okay, I didn't show it here, but anyway, there's a command called mph save. You can just mph save file name. I can say random file dot mph something. I can't remember if whether I need to have this.
Yeah, that's
Why? Okay. mph model. I can't remember if this is the right syntax, but well, anyway, let me see. Let me try. Can I open a? Yeah, just search mph save. And there are a lot of good resources for you to use. See, yeah, you can see mph save model file name. If you don't specify the directory, it will just save to the default position. So in here, let's say, well, this is a function. I can say, okay, I'm creating this AA as 1.5, right? Oh, sorry, my bad, AA, right? I can say, okay, single layer 1.5. And now because I have this mph save in here, so it should be able to like save the file for me. If I run it after a while, I should be able to see a new mph file. After, there you go. Now, let's say, if you open this file,
like all like also like even when you already open from like program.
yeah, yeah,
Loading.
super slow.
But in other softwares, when
You already have
you
your
already have a file open, you can easily open another, but this is typically like.
Yeah, yeah. But anyway, as you can see here, right? Parameters is directly set at 1.5 times R reference. And then you have all of these results available. You have all of these results available in here. So you can basically create any file in the Matlab, save it as mph. And in some cases, in some of the projects I've done before, I've done some optimizations, right? So in a normal optimization, you're calculating the value of a function, right? So now I'm setting the simulation as my function. So let's say in this Matlab file, I'm creating a lot of structures with Helmholtz resonators with different sizes, but all of these sizes, okay. Okay, anyway, yeah, with this optimization, right, I can have all of these, let's say hundreds of different set of parameters for the size of each individual Helmholtz resonator. I want to find, okay, what is the best combination of all of these sizes to give me the acoustic property I want. So I put in everything into a MATLAB optimization tool, and then just set this set this simulation as my function, and then use this as a normal function to find the minimum value, minimum cost, and then it can do the optimization for me directly.
Matlab optimization is another aspect of Matlab.
Yeah, MATLAB has an optimization toolbox. It's pretty good. Yeah, it can handle the normal optimization needs, I think, for a project. Yeah. Anyway, there are a lot of things to play with. Yes, exactly. And COMSOL, you can just treat COMSOL as a normal MATLAB function you want to create, right? And then you can call it like multiple times without opening up this console. Actually, it runs faster than directly running inside console. Yeah, because it doesn't have to like open this graphic interface for you. It will just run the code in the background and spit out the whatever number you want, and then just delete everything. Yeah, until you find a good combination you want to save it, then it will save it. Yeah. Yeah. But just remember to deactivate saving, because if you want to like run it 100 times, it will save 100 files. That would be a disaster. Another thing to keep in mind here is COMSOL is kind of like stupid. Because like for example, it will not clear the model after each run, so it can use up your memory pretty fast. So if you have go into these detailed things, what you can do is just create an empty model every single time before you run the new simulation, and it would just wipe out all the previous models, yeah, for you, and you start fresh, then your memory should be good. Other than that, it should be okay. Also, the Matlab is not well. COMSOL is not very good at parallel computing. So let's say if my computer has 4 cores, I can in principle do the parallel computing, but these model names will be conflicting each other. So to do that, what you can do is save as a MATLAB file, right? In the and copy and paste into 4 different copies with a different name. And for these 4 parallel calculation, you call different functions. That can solve the problem, but that will introduce more problems, as you can tell. Yeah. Yeah, but anyway, even without the parallel computing, it is still a pretty good tool to have, right? Because now you can use your COMSOL file as a function inside MATLAB. You can do many things with.
So these the optimization tools that they are really like this.
Oh no, the optimization tool, you just like find it in MATLAB. How can I? Yeah, you can just Google how to use the optimization toolbox in MATLAB. Optimization. Yeah. You can see how to use these. What type of functions do they provide? They provide some very basic optimization method like pattern search, Newton's method, like based on gradient, genetic algorithms, PSO probably, annealing definitely, yeah, simulated annealing process definitely, yeah. Anyway, it provides a lot of different type of optimization functions you can use. Yeah, I think they're pretty cool thing.
Just make curious now, for the kind of project that I working on, the batteries, is it possible to?
I'll stop sharing. Is that okay?
Can I stop this video before?
Yep.